Now let us discuss the first theorem on normal subgroup. The theorem states like this: a subgroup H of a group G is a normal subgroup of G if and if X into H is equal to Hx for every X belongs to G. That is, if H is a normal subgroup of G, then XH is equal to Hx. And if H is equal to Hx, then in that case H must be normal. So let us prove the first part, that is this one. Let us assume that H is a normal subgroup of G. Then by definition of normal subgroup, X inverse must be contained in H. So let us name this as equation 1. This holds for every X in G. If it holds for every X in G, then in that case, if you replace X by X inverse and X inverse by X, then that also will hold. Why? Because X belongs to G. It implies that X inverse also is an element of G, as G is a group. So it holds, since it holds for every X in G, and in particular X inverse also is an element of G, so replace X by X inverse and X inverse by X, then you'll get X inverse Hx is contained in H. Now from this one, you multiply on both sides but on the left by X. X inverse Hx, this is contained in XH, or EHx is contained in Hx. Since XX inverse is equal to E, the identity element in G. And this will imply that HX is contained in XH, since EH is same as HE, which is equal to H. Now next, multiply on both sides but on the right side now by X inverse. So this implies that X inverse, this is contained in XH X inverse, which implies that HE is contained in XH X inverse. And this implies that H is contained in XH X inverse. Name this as equation 2. Now let us compare equation 1 and 2. In equation 1, I have XH X inverse is contained in H, but in equation 2, it is the other way. H is contained in XH X inverse. Now 1 and 2 will be possible only if H is equal to XH X inverse. This is from the property of group A is equal to B if and only if A is contained in B and at the same time B is contained in A. And from here, multiply by X on both sides but on the right. This is XH X inverse X, which implies that HX is equal to XHE, as X inverse X is equal to E. And this gives you XH is equal to HX is equal to XH. So this proves the first part, that is, if H is a normal subgroup of G, then XH is equal to HX. And conversely, suppose HX is equal to XH, then I need to show that H must be a normal subgroup of G. So here it implies that if you multiply on both sides by X inverse but on the right, so you get X inverse, this is equal to XH X inverse, and this implies that H is equal to XH X inverse, because X inverse gives you E and HE is equal to H. So now H is equal to this one, which means that XH X inverse is contained in H. Again, by this property, A is equal to B if and A is contained in B and B is contained in A. So H is equal to XH X inverse will implies that XH X inverse is contained in H. And this implies that by definition of normal subgroup, XH X inverse is contained in H. It means that H is a normal subgroup of G. So this proves this theorem, that a subgroup H of a group G is a normal subgroup of G if and if XH is equal to HX. Now let us come to this next theorem. The intersection of two normal subgroups of G is again a normal subgroup of G. That means if H1 and H2 are, if H1 is a normal subgroup of G and H2 is a normal subgroup of G, then we need to show that H1 intersection H2 is a normal subgroup of G. So this we have to use the definition of normal subgroup. So if I can show that, consider this one as a single H, if I can show that for every X in G and for every H belongs to H1 intersection H2, if X inverse belong to H1 intersection H2, then I can conclude that H is a normal subgroup of G. So here let X belongs to G and H belong to H1 intersection H2. This will imply that X belongs to G, and now H belongs to their intersection implies that H belongs to H1 and at the same time H belongs to H2. So if you take this first one, X belongs to G and H belongs to H1, it will imply that X inverse belongs to H1. Why? Because H1 is a normal subgroup of G. You can write here as H1 is a normal subgroup of G. Similarly, X belongs to G and H belong to H2 will implies that X inverse belongs to H2. Why this is possible? Again, because H2 is a normal subgroup of G. So H2 is a normal subgroup of G. Now, this is equation 1 and this is equation 2. You can see from equation 1, X inverse belongs to H1. And from 2, we have X inverse belongs to H2. So which means that X inverse from 1 and 2. 1 and 2 will implies you that X inverse belongs to H1 intersection H2. For every X belongs to G, H belongs to H1 intersection H2. So by definition of normal subgroup, if X inverse belongs to H, then it implies that H is a normal subgroup of G. But here, what is capital H? It is this one, H1 intersection H2. So which means that H1 intersection H2 is a normal subgroup of G. However, if we replace the intersection by union, then the result will not be true. So for that one, we can take this particular example. However, if intersection is replaced by union, then the result is not true. Take H1 which is equal to 2 set, which is a normal subgroup of G which is equal to set of integers. H2 is equal to 3 set. This is also a normal subgroup of G which is equal to set. But what is H1 union H2? This will contain the element 0, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 5, plus or minus 6, plus or minus 8, and so on, which are multiples of 2 or 3. Now, separately, 2 belongs to H1 because H1 contains this element 0, plus or minus 2, plus or minus 4, all multiples of 2. And H3 contains the elements 0, plus or minus 3, plus or minus 6, plus or minus 9, which are multiple of 3. Now 2 belongs to H1, 3 belongs to H2. Then 2 plus 3, which is equal to 5, does not belong to H1 union H2. So this implies that H1 union H2 is not even a group, a subgroup of G is equal to set. Therefore, if we replace intersection by union, then the result will not be true. So this will be the example for that one. So I hope it is clear now regarding these two theorems and also this example. If it is not clear, you please let me know.